linear regression. One thing we didn't really talk about, though, is we didn't talk about the. Well, I mentioned to you, anytime you make predictions in linear regression, you're making predictions about what's going to happen on average. But within any single person, there can be a lot of variability, right? So we did examples where we predicted someone's GPA based on their absences, but individuals are going to have a high variability in their GPAs, even with the same amount of absences. And so the same thing happens when you're going out and you're taking samples from a population. So the idea is, okay, so you go out, and again, you don't have to write this down again because I've done it, but, right, so we know in the big picture, we're generally not looking at the population. We're looking at some sample from the population. And so, we talked about calculating statistics, but then in the last one, we did a little bit of this, where you estimate parameters, because those parameters are the things that describe the population. Okay. Well, what happens, though, is that in that step, from going from your sample information to making estimates or predictions about what's happening or what's going to happen, there's that variability involved. And it's like even if your sample is a well-designed sample, you still haven't observed the population, and someone else could go behind you and take another really well-designed sample, and they could get different results than you because we observed different people from the population. And so what happens is in this step right here, you get a lot of, well, actually I should say really, in the sampling step, you are going to experience a lot of variability, right? I told you there's this thing called sampling error, and it's unavoidable. It's just the simple fact that you're not observing everyone means you're going to make them, you're going to have some error in your estimation. And so in this step, where you actually go to make estimations, then what happens is you introduce a lot of uncertainty into the equation. So as soon as I can say whatever I want about my sample, I can describe it and be 100%, right about what I'm saying, but as soon as I try to take that information and make predictions about what's happening or what's going to happen, now there's uncertainty involved because I can't be 100% certain what's going to happen in the future or what's really happening at the population. Well, if you're going to have uncertainty, then we want to find a way to quantify that uncertainty, and so we have to spend some time talking about probability because that's really what probability is. Probability is it's a way to quantify uncertainty. Or quantify or maybe explain. We want to have some way of saying, okay, I know that my estimation has some error in it, but at least is there some way I could quantify how much error? Or could I have a good idea of how close I am to the truth? And probability is what's going to help us quantify that uncertainty. So we got to spend some time talking about probability. It kind of feels like an aside for the whole course, and it really kind of is, but it's just we have to understand probability in order to do the inference later on in the class. So we'll start with some simple examples and then maybe look at some more complicated examples. So here we have an example. So here's the top 5 elected officials in our state. And let's say that you're going to randomly select 2 of those to interview or something. I don't know. What's the probability that you're going to end up with the treasurer in your sample? You're doing random selection, right? So it's like drawing their names out of a hat or using a software program. What's the probability that you end up with a treasurer?
1 out of 5.
Maybe. That would be true if you were picking one person. But see, I'm actually picking 2 people. Is it 2 out of 5? Because once I pick my first person, it might be the treasurer, but it might not. But then I don't have 5 people to pick from anymore. I only have 4 people to pick from. So is it... Yeah, so when you're talking about probabilities, you need to think about all of the things that could happen. Okay? So if I'm going to pull 2 people out of a population of 5 people... Okay, well, how many different ways could that occur? There's not just 5 ways it could happen, because any one person could be paired up with any of the other 4, right? And so it's not so straightforward. It's not just 5 ways to pick 2 people.
Is it 9 out of 10?
Well, let's try to tackle how many ways to do it first. How many ways can you pick 2 people out of 5 total? Anybody got a guess? Maybe 25? How many ways can you do it?
10.
It is 10, actually. How do you know it's 10?
Because it's 2 times 5.
It's not because it's 2 times 5, but that's a good guess. The answer is 10, though, I think. I believe the answer is 10. But not for that reason, and that's okay. The answer is 10. Anybody know why? Now, in this case, you could actually list all the possibilities. It's not that hard, right? We could list every possible sample, okay? Because if you think about it, okay, so let's say it's possible you could get the governor in your sample. That's one possibility. And he could get matched up with who? Yeah, it is a count. Yeah, there's some counting strategies involved if you wanted to, yeah, which we will talk about. Yeah, but the governor, he could be paired up with a lieutenant. The governor could be paired with the secretary. The governor could end up paired with a treasurer, or the governor could get paired with the attorney general. All 4 of those are possibilities when you go sample 2 people, right? But you're not guaranteed the governor in your sample. You could also end up with the lieutenant and some other options. Now, we already did lieutenant and governor, right? So we don't need to recount that.
But the lieutenant could be first, and then the governor could be second.
Well, let's say for the sake of sampling, I don't think it matters which one comes first. Sometimes it matters, and we will talk more about that at the end of this module.
Okay.
But let's just say right now you're just going to sample them and interview them. It doesn't really matter if you interview one first or one second. You're going to talk to the same people. So the lieutenant could be paired with the secretary, but could also be paired with what?
Treasurer.
The treasurer or the attorney general, right? Of course, then what do we have to consider?
Secretary.
There's also, you could end up with the secretary, who we've already paired with the lieutenant governor and the governor. So, but they could be paired with the treasurer or the attorney general, right? And then the last option that we haven't gotten is, it's possible you could end up with the treasurer and the attorney general, right? So these are all the possible ways that your sample could look like. All right. Now, how many ways are there?
10.
Yeah. So there are 10 possible ways, possible samples. Okay. Now, this collection of all of these possible outcomes, this is in probability, this is what we would call the sample space. All right. It's like this is all of the possibilities that could happen going into it. So before I even perform this experiment, I know that there's 10 ways that my experiment or that my sample could look like when I come out of this. Now the question is okay, well then, what are the chances? My first question is, what are the chances you end up with the treasurer in your selection? That was my one up here. The treasurer in your selection. Well, how could you figure out your probability of getting the treasurer then?
4 tenths.
Yeah, you just go through and you say, well, here is the treasurer. The treasurer is here. The treasurer is here. The treasurer is here. The treasurer is there. Okay. So how many ways are possible? There's 4 ways to do it out of 10 possibilities. Actually, this one, someone did say 2/5, so you were actually technically right. This one does end up being reduced to 2/5, or a 40% chance on that one. But maybe not for the reason you thought it was 2/5. All right. So there's a 4 in 10 chance, which just reduces. Or you could, so probabilities can be written as fractions. They can be written as proportions. They can be written as percentages, right? All of those are equivalent forms of the same value. So it's a 2 in 5 chance, or a 40% chance, or a 0.4 proportion. Okay. Now here, what are the chances that you don't get the governor? What are the chances you will not see the governor?
6.
Yeah, you say, well, 4 of them have the governor, right? And then 6 of them do not. These 6 don't. So 6 out of 10, or 3/5, which is 0.6. Either one of those is fine. Typically with probabilities, we'll work with a proportion form. Not the fraction's fine, but for calculations, decimals are a little easier. So we'll typically stick with proportions. Okay. Questions about that? Does it make sense how we came up with those numbers or why they describe the chances? So this is the most general definition of probability, or how to calculate a probability. is the number of ways an event can occur divided by all the number of possibilities, basically. It's like, how many ways could it happen? How many ways could what I want to see happen? And then you look, and then the probability is going to be the ratio between those. So we say that the probability of an event so the probability that an event occurs. Okay. It's a ratio, it's a fraction, it's a proportion, and it's the number of ways that the event can occur divided by the number of possible outcomes. Okay. So there's a whole bunch of things that could happen. There's there's a bunch of ways that the thing I want to see could happen, and the probability is going to be the ratio between those two. All right. Actually, I want to look at something real quick to make sure I got my slides in order. Okay, cool, we're good. All right, so we can look at we'll look at another example here. All right, so let's say you're rolling two six-sided dice. I drew the table for you here. But if you're rolling two six-sided dice, typically speaking, and I should clarify here, let's say you're rolling two six-sided dice, and what you're going to do is you're going to observe the sum of the two, because that's typically how two dice getting rolled works. Typically, you're going to add up the values. Okay. So over here, I made a little table to kind of show you that. How many possible outcomes are there when you roll two dice?
36.
Yeah, there's 36 ways, because the first die could come out 6 ways, and the second die could come out 6 ways, and you can see inside the table what that produces is it produces 36 possible outcomes, right? And one way we'll talk about counting later. It's just that you can, if one thing can happen a certain number of ways, so this is the number of ways that die 1 can land, and this is the number of ways that die 2 can land, then together the number of ways they can interact is going to be 6 times 6, which is 36. Okay.
Where the 5 and the 2 meet, it says 4.
Oh, I probably just made a typo in there. Where'd I go?
Like in the 7.
Oh, yeah, that's supposed to be 7. And I copy-paste that thing all the way through the slides. So it's all good, though. That should not be a 7. Right? But the way the table works here is like inside it shows you something, right? So if you roll a 1 and a 1, you're going to get your score is a 2, right? If you roll a 1 and a 2, it's a 3, or a 6 and a 5, it's an 11. And there's a pattern there you can see that goes down the diagonals. The same number follows the diagonals. Because as one's going up, the other's going down. Anyways, okay. Does that make sense? 36 ways it can happen. So then you can start to measure the probabilities of certain events happening when you roll 2 dice, as long as you know how many ways it can happen. All right, so now we know it's 36. So I'm going to fix this again. This should be a 7. All right, so if I'm rolling 2 6-sided dice, what's the probability that the sum is 8? What's the probability that I roll an 8, basically? Yeah, so you go to your table, and I say, okay, well, what I need to do is, I know that to calculate probabilities, I need to figure out, well, how many ways can I get an 8, and how many ways can I roll the 2 dice, right? Well, there's 5 ways to roll an 8, there's 36 ways to roll the dice, and so that would be the answer. It's not reducible. If you had to approximate it, what does that come out to be? 5 out of 36? Anybody want to do that for me? 1, 3, 8, 8, 8, 8, 8, 8. Yeah, and typically speaking, I'll generally round my probabilities to 4 decimal places, only because later we're going to use some tables and stuff that have probabilities, and they're just rounded. They're usually rounded to 4 decimal places. So yeah.
Are you going to give us a table for the test?
For what? Like this one?
Yeah.
Probably not. Like, so if I asked you a question about rolling dice or something, I would expect that it's not a very hard table to recreate, because it's just a table with 1 through 6 on either side, and the sum of them in there. But yeah. Okay. All right. What about the probability that the sum of the dice is less than 8? Yeah, so less than 8 can happen a lot of ways,
21.
right? Everything less than 8. So how many ways can it happen? It can happen. Someone added them up. What did you say? Was it 21? Other people get 21? Is that true? Okay. So there's 21 ways to do it out of 36 total. So you're just adding up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just adding up all the ways it could happen. 21 out of 36. That's divisible. They're both divisible by, 3? So it'd be 7 out of 12. What does that come out to be if you approximate it?
0.5833.
0.5833? There you go. So it's about a 58% chance that you'll roll an 8. Right? So, there's about a 14% chance you roll a 5, a 58% chance you're going to roll something less than 8. Okay. So, what does that actually mean? I mean, what does it mean that you have a 5 in 36 chance to roll an 8?
That if you roll the die 58 times out of 100, you'll probably get below an 8.
So, yeah, so it means, you're talking about you're talking about this one.
Yeah.
Yeah, so it's like, if you roll a dice 100 times, you would expect to see a number less than 8, like 58 out of 100 times. Is it going to be 58, though? Does it have to be? It doesn't have to be. It's not guaranteed. 7 out of 12, does that mean if you roll it 12 times, you're going to see it happen 7 times? If I roll 36 times, am I going to see 5 8s? I could. Is it guaranteed? No.
Could you just say that if you rolled that, like for the first one, would you say if you roll 2 dice for 2 dice, one time you'll have a 0.1389 chance of getting an 8?
That's a way to say it. I mean, yeah, that's a way to report the probability. That's true. But what does that actually mean? Because if I roll the dice one time, I'm either going to get it or I'm not.
About 14% chance of getting it.
Yes. But when I roll it once, I'm either going to get it or I'm not going to get it. So what does 14% have to do with anything?
You have a chance.
Yes, you have a chance.
This is going to be like a face palm moment, isn't it?
What's that?
This is going to be a face palm moment when you say it, and then everybody's like, how do you not think of that?
No, it's not that simple. I don't think it's more complicated than it seems.
Like, you're likely to roll an 8 5 times out of 36?
Ooh, no. That's completely different, actually.
Sure.
That's a different type of problem. I guess my question is like, that if you roll it 36 times, you're probably not going to actually see 5 8s, right? I mean, you could, but you actually probably won't.
Are you just looking for the word on average?
Well, so that's part of it. So it's like the probability itself means, it's almost like it means something, but it's not a guarantee, right? So what's the point of knowing the probability of an event? On average, it has something to do with it, yeah.
Know your chances of what you want occurring.
Yeah, so it's not useless because one thing probabilities help us do is compare likelihoods. So it's very clear that if I was a gambling person, I should take the second bet instead of the first bet. Okay. So first off, we can use probabilities to judge how likely an event is, or which events are more or less likely than others to occur. But the number can't be useless. But it kind of feels useless when you think about it because it's like, okay, well, the probability is 7 out of 12, but I know if I roll it 12 times, I'm probably not going to see what I want 7 times exactly. Okay. So what does that mean? Like 14%, what does that mean? 58% probability, what does that mean? I'm looking at let's look at the first one, right? So 5 out of the number of ways to roll an 8. It's 0.1389. There's about a 14% chance it happens. How am I actually going to see 14%? Am I ever going to actually see it happen 14% of the time?
Maybe after a large amount.
Yeah, that's the thing. That's what probabilities are. They're a measure of long-term behavior. So you can talk about them in the short run about what's more likely, what's less likely. But in reality, in the short run, these things are really unpredictable. Like, for example, if I do the experiment one time, I'm either going to see it or I'm not going to see it, right? I'm either going to, in one experiment, it's either going to be 0% of the time or 100% of the time. I can't observe 14% when I only do it once. It's a large sample. Yeah, so what probabilities are is they're a long run proportion. Okay, so that's what the probability is. So the probability of an event, is the proportion of times it will occur in the long run. Actually, I've got to make sure I'm in here real quick. I think I might need to add one slide. I think I want to go. Oh, okay, I got an idea actually. I want to do it. We're going to talk about something called the law of large numbers really quick. I can add that slide in there, but I'll go back to this one for you now. Okay. So what happens is, you can imagine. Let's think of an example like a simple one, like flipping a coin, right? If you flip a coin, what's the probability that it lands on tails? It's 50% basically, right? It's a 50-50 shot. It's going to happen half the time. Now, if you think about, if you flip a coin though, so like if you were to make a chart and you were to plot like the number of flips and then the proportion of tails, then, if here's 0 and here's 1, it's supposed to be about 50%. Okay? Right? But what happens is you're not probably actually going to see 50% in a short number of experiments, right? So if I do if I go flips, right, and then I compared like proportion tails. So let's say that I flipped it once, and then I got let's say I flip it once and I get tails, right? Well, then my proportion starts at 100%. Well, I could flip it again and get tails, and then I'd still be at 100%. But let's say the third time I flip it, I get a heads. Well, what's my proportion of tails? It's like 2/3, 67%. So in the short run, your proportion isn't actually going to match the probability, right? It's going to fluctuate. So it's like in the short run, there's variability in these events. But what will happen is that in the long run, as the number of flips gets higher and higher and higher and higher and higher, then what you're going to see is that the proportion observed should converge to the actual probability in the long run. Yeah, it's a limit. What was I going to say? Oh, here's the reason. So this is something called the law of large numbers, and so what we're seeing here is this 50% right here. This is something called a theoretical probability. Right? It's like that's what should happen in theory in the long run. But over here in this column, like in my sort of imaginary experiment, these are what we call empirical probabilities. Okay? And if you remember, what does empirical mean from the empirical rule? I told you what it meant. It means observed, right? So theoretically, a coin should pop up on tails 50% of the time, but in practice, if you actually sit down with a coin and you flip it a bunch of times, you're going to get a proportion different than 50%. Your proportion from your experiment would be considered an empirical probability, or an empirical proportion, but the 50% is a theoretical probability. It's calculated from properties from the sample space. Okay. So I'll write that down on the next slide. So the theoretical probability, that's the probability Actually, I'll say that's the proportion. That's the proportion of times an event should occur in the long run, and it's based on properties of the sample space. Okay, so that's what should happen. And if you know what the sample space looks like, it's not that hard to calculate the theoretical probability. Like, so for rolling the dice, I knew all 36 options, so I can know exactly what the theoretical probability of rolling an 8 is. Then the empirical probability, so the empirical probability of an event, that's the proportion of times it happens in a fixed number of trials. An event occurs in a fixed number of observed trials. Okay, so now what I showed you on the last slide, though, is as the number of trials gets really, really big, what should happen between those two values? Like what you observe and what's supposed to happen? They should get closer and closer and closer to each other. And they will. And the reason is so go back to flipping tails. Right? So let's say that if I were to make a chart, this is like a theoretical experiment. Let's say that I flipped it, say, 20 times, and out of those 20 times, maybe I saw, maybe I didn't see very many tails. Maybe I only saw like 5, right? What would be my proportion of tails if I only got 5 out of 20? It's possible. Okay. What would it be? It would only be what? 0. I think it'd be 2.5, right? Yeah, 1/4, right? So out of 20, how many tails would you expect to see based on the theoretical probability? Should see 10 out of 20, but we actually saw 5 out of 20. We were off by 5 from what we expected to see. Now, what happens if I do 100 flips and I observe 45 tails? What's my proportion? Right? So with the number of trials increasing, I'm off by the same number of what I would have expected. Here I would have expected 10, and I saw 5 less than that. Here I would have expected 50, and I saw 5 less than that. But what's happening to the proportion? It's getting closer. I mean, and you can imagine, let's say you did this 10,000 times, right? Well, out of 10,000 flips, I'd expect 5,000 tails. But if you saw 4,995, well, what's your probability empirically? 4,995. You're basically at 50%. So what happens is that the variability in the short run, it makes your proportion, very different than what you expect to see. But in the long run, even if you see a little variability, the sheer number of trials, it eats up that variability to the point where the proportion is going to converge to 50%. And that's what the law of large numbers says. So the law of large numbers, or I'll just abbreviate it LLN, law of large numbers says that as the number of trials or observations approaches, infinity, or gets bigger and bigger. So as you take more and more trials, then what's guaranteed to happen is that the empirical probability is guaranteed to do what?
Match it.
Yeah, it will approach the theoretical probability. Guaranteed. Yeah, that's what the law of large numbers says. So probabilities, they help you judge the likelihood of things in the short run, But in the short run, events with a probability have a lot of variability in them. It's the long run predictability, though, that we rely on when we're trying to judge the likelihood of events. And this is what this is telling us is like it has something to do with sampling, because if you ask me like how many samples should you take to answer a certain question, the answer is always as many as you possibly can. And the reason you should always take as many as you possibly can is because the more observations you make, the closer you're getting to the truth. That's the idea, right? And another really powerful. This seems like really kind of straightforward, probably. Like, why do you even need to like define it and give it a name? But think about this. Do you always know the theoretical probability of an event occurring? Can you always find the theoretical probability of an event occurring?
I'd say like a plane crashing.
Yeah. What's the probability that a plane crashes? Right? When I get in a plane, what's the theoretical probability that it's going to arrive where it's supposed to arrive?
You can figure it out though, right? Like take out the number of plane rides versus crash.
But that's an empirical probability because it's been observed over a lot of plane rides. Like, what is the, like, there's no, it's not like the universe, I mean, maybe it is. I don't know because I'm not God, but maybe it's like, maybe there is some theoretical probability out there that controls everything. But do we know it? No. What's the theoretical probability, like, I hate to use the example but what's the theoretical probability that I get in a car wreck on my way home? Now I'm going to get a car wreck on my way home. That's what I'm trying to, so shouldn't talk about it. But what's the theoretical probability of that happening? It doesn't exist. Right? But if you observe enough data over time, like you're talking like the plane crash example, if you have enough airplane, takeoffs and landings, by the time you reach 1 million or 10 million or 20 million or 1 billion, flights, at that point, your empirical probability should be pretty close to the theoretical probability, and you can treat it that way. So that's the great thing about the law of large numbers. It says you don't actually need to know the theoretical probability of an event, because if you observe it over enough trials, you can be pretty sure that your empirical probability is the theoretical probability.
So you won't always know theoretical.
Exactly. That's the thing. And the reason is because there is no sample space for a lot of events. Like, what does the sample space look like for my trip from here to home? It's an infinitely large sample space because there's infinitely many things that could happen between here and there. It could be raining, it could be windy, there could be a drunk person on the road, there could be a cat in the freeway. I mean, you don't know, right? So the sample space is infinitely large. So anyways, that's the law. That's a long way of explaining what probabilities are. So they're meaningful, but they're most meaningful in the long run. Okay. I feel like we got one. All right, that's good though. So if you're talking about the probabilities of events, there's a couple properties of probabilities. So the probability of an event, it always has to be between 0 and 1. Okay, probabilities cannot exceed 1. And they cannot exceed or can't go below 0%. Why can't probabilities go over 100%? You can't, nothing can happen more than 100% of the time. Because 100% of the time is always guaranteed. If something has a probability of 1, then it's guaranteed, right? The probability that you were in this classroom 5 seconds ago is 100%. It happened, right? But you can't go over that. And then you can't go below 0% because, 0% means it never happened or it never will happen. So, the other property is if you have, how do I want to say this? If you look at the sum of the probabilities of all possible outcomes, they should add up to what?
One.
Yeah. So that's the way I'm going to say it for now. We're going to get some notation in here pretty soon to make it a little easier to write that, but nothing can happen more than 100% of the time. Nothing happens less than 0% of the time. And if you consider every single possible outcome, all their probabilities should add up to 100%. So this is like an example of this. This is like, what's the probability that you roll any number between 2 to 12 on our dice, right? Well, that's every single possibility. And so it's just all of those probabilities together should add up to 100. If you take all the, anyways, you get the point. All right? So if you're working on a problem and you get a probability that's more than 100% or less than, or it's negative, that's a pretty good sign that you probably did something wrong. Okay, you can't have probabilities outside that range. All right. So I've used some of these terms, but just to better define them. Okay. So what happens is outcomes. These are an outcome is a possible result from a trial or observation. Okay. The sample space, we already talked about that. The sample space is the collection of all possible outcomes. And then when I'm talking about events, when I say an event, what I'm saying is this is a collection of one or more outcomes that I'm interested in. You can ignore the section thing down there. It's not accurate, but excuse me. Okay. All right. And so you have different levels. So if you go back to, and maybe I have one here. If you go back to, like, say, the dice rolling example, the whole collection, all 36 are the sample space. Each one of those 36 is a possible outcome, but like events can consist of multiple outcomes. So dice being less than 3, that's an event, but it consists of 21 outcomes. All right. So then, just to make our lives a little bit easier, we have some notation. So typically events. So typically events are, we use capital letters. All right. So like as an example, I could, like earlier, is like rolling an 8. So I could say that call A to be the event that the sum of the dice, A is the event that the sum of 2 dice is 8. Okay, so I give it a capital letter just so I don't have to keep writing that over and over and over and over. Okay. Some things we have set aside as special. So like the sample space. The sample space we always call capital S. Okay. And then probability notation, the way that works, it's kind of like function notation in algebra, or like f of x, g of x kind of notation. So if I want to say something like the probability that you roll an 8, okay, then I would write that as, you could write that as the probability that you roll an 8. So it's like P of whatever you're interested in observing. And then if you've actually already given your event a letter, like we did up there, we would just denote that as P of A. So I defined A as the event. The sum of the 2 dice is 8. So if you see P of A, it's telling you to calculate the probability of that event. That's probability notation. Okay? All right. So another way we could have written the I'll do it in a different color just because going backwards. But another way we could have said this is that for any event, the probability of A has to be between 0 and 1. That's another way to write that. And then another way to write the second statement would be that the sum of all the probabilities has to add up to 1. So you could write it that way, using that summation notation that way. It's just it's mostly just for convenience, so we don't have to write so much junk. All right. So far, so good? Okay. So let's look at another example. If you don't know what a deck of cards looks like, you should Google it and figure it out, because I think there might be some examples on the quiz with cards. I can't remember if there is or not. But it just makes a really easy example when you're looking at probabilities. So 52 cards, 4 suits, 13 cards per suit. You've got reds. 2 suits are red. 2 suits are black, right? So half of them are red, half of them are black. And then the 4 suits are diamonds, hearts, and then clubs, spades.
3 space cards.
Yeah, yeah, exactly. And so there's 2 through 10. Well, there's ace, 2 through 10. Then you got jack, queen, king. Face cards are considered cards that literally have faces on them. Jack, queen, kings are faces. Ace isn't considered a face card, at least not for the sake of this class. So you could define this. Let's say that you're going to randomly pick a card, and I'm interested in some of these events. So A would be that the card is king, B is the card is a heart, C is that the card is a face card. Okay? So typically if we have events and we know what the sample space looks like, we can list out the, I'm not going to list the sample space, don't do that right now, because the sample space is very big here, right? The sample space would be a lot of stuff, right? It would be like the ace of hearts, the 2 of hearts, all the way up to the king of hearts, right? Then you'd have the ace of diamonds all the way up to the king of diamonds, and the ace of spades all the way up to the king of spades, and then the ace of clubs all the way up to the king of clubs. Yeah? I'm not going to list them all out, but how many would be there? Yeah. So the sample space would be a big collection of 52 possible outcomes. All right. How about A? What would A look like? The card's a king. How big is that going to be? There's only going to be 4 possibilities there. You have the king of hearts, the king of diamonds, the king of spades, the king of clubs. Right? 4 outcomes. All right. How about B? How many are going to be there? 13. Because there's 13. There's, the ace of hearts, the 2 of hearts, all the way up to the 10 of hearts, the jack of hearts, the queen of hearts, and the king of hearts. Okay, so there's 13 cards in that outcome. How about C? It's a face card. How many of those are there?
12.
Yeah, 3 per suit times 4 suits. So there would be 12, right? There you'd have the jack of hearts, queen of hearts, king of hearts, and then you'd have the same for diamonds. You'd have the same for spades, and you have the same for clubs. So there'd be 12 there, right? And so if you know what the sample space looks like, and you know all the ways that your event can occur, then probabilities are pretty straightforward, right? So I could calculate the probability of A, B, and C really easily, which I was going to do here, right? So the probability of A occurring, what's it the probability of? It's the probability that the card is a king. What's its probability? 4 ways it can happen out of 52. And that reduces to 1 in 13. Yeah? You can make it a decimal if you want. I'm not that really worried about it right now, though. Just giving you some notation experience. Probability of B, that's the probability of a heart. How many are there? 13 out of 52. Or another way to say that would be 1 in 4, which makes sense because there's 4 suits. Probability of C, again, it'd be over 52. How many were there? 12. Makes sense. Then that reduces to what? Is it 3 out of 13?
Yeah.
Yeah, and that makes sense, right? Because there's 3 face cards for every 13, because there's 3 face cards for every suit. All right? Perfect. So you got sample spaces, if you can construct them, it makes life nice because then when you start talking about events, you can figure out exactly how many outcomes are in that event, and then calculating the probabilities is very straightforward.
Do we have to reduce the fractions?
Should, yeah. I mean, honestly, most of the time when you deal with probabilities, you're just going to put them in decimals. So this would, I don't know, what did these come out to be? 1 out of 13 is 0.0769. What's the next one?
0.25.
Oh, yeah, that one's a 0.25. That one's easy. What's this one?
0.2308.
If you round? Something like that. Okay. So, yeah, normally probabilities are reported in percentages or proportions. But if you report a fraction, you should, simplify it. That would just make the mathematician and your teacher happy. But you could also just turn it straight into a decimal, and then you don't have to worry about reducing. Okay. So, actually, I think that's a good place to stop on a Thursday. So that's the general ideas behind probability and notation. Then on Monday, we're going to look into some more complicated types of probabilities.